Hi there, guys. My name is Wilfrid, and I'm a senior math tutor. And today I'll be covering 10 questions related to calculus and limits and derivatives. So a little bit backstory upon myself. I graduated from McMaster with a major in biochemistry and a minor in mathematics. And yeah, let's just jump right into these questions. If you have any other issues or problems with your homework, tests, or assignments related to calculus or mathematics or algebra, please submit them through OneClass and we'll get to them as soon as possible. Okay. So the first question reads, how do you find the derivative of a given equation? So how do you find a derivative of a function? First of all, we need to define what a derivative is. So there's multiple ways to define a derivative, um, but I like to define the derivative as such. Let me find the right pen first here. Okay. Okay, here. So a derivative, we write, so if we have a function, let's say f of x, for example, then our derivative is going to be f prime of x. And it is simply the limit as h approaches to 0 of this expression here. So this is the derivative of a function at point x, which is the limit as h approaches to 0 of f of x plus h minus f of x divided by h. So the limit basically calculates the behavior of the function at the given point, and it basically tells us, oh, what is the function going to approach as h comes to be less than tends towards 0, basically. So this is kind of the definition of a derivative. Another definition that we can use is f prime of, let's say, a of the limit as um, x approaches 0 of f of x minus f of a over x minus a. So this is another way that we can define a limit. So basically, we're trying to evaluate the derivative of a point, and we're calculating the limit of it as the function approaches that point. So that's what these two definitions tell us here. Okay, so we're going to use the first definition to calculate the derivative of our example here. So the junior tutor gave us an example of f of x equals x squared plus 2x plus 1. Okay, so with this in mind, we're going to use the first definition here. So we need to calculate what f of x plus h is. Okay, so f of x plus h, we're just going to plug in x plus h into each of our x's in our function here. So we have x plus h squared plus 2 times x plus h plus 1. All right, so that means that um, f of x plus h minus f of x divided by h is going to be given by x plus h squared plus 2 times x plus h plus 1 minus x squared plus 2x plus 1 divided by h. And this simplifies to 2xh plus h squared plus 2h divided by h. Cool. So if we were to simplify this even further, we can get rid of all the h's on the numerator and the denominator. So we're just left with 2x plus h plus 2. Okay. All right. So now we're going to evaluate the limit of this. Okay. So the limit of as h approaches 0 of 2x plus h plus 2. What is that equal to? So we're just going to sub in h equal to 0 here, and we're going to find the limit. And that's going to equal 2x plus 2, which is the derivative of this function, x squared plus 2x plus 1. So by using this limit definition of a derivative, we're able to calculate the derivative of this function. And maybe later in the lesson, we'll cover some of the tricks and techniques that we use to calculate the derivative of different kinds of functions, like power functions, the product of functions, the sum of functions, and the division of functions. So we're able to do that with different techniques other than calculating the limit, using the limit definition of a derivative. All right. So other than that, the solution is correct. Good job. All right, so question number 2 reads, find the slope of the tangent line to the parabola y equals 4x squared, 4x minus x squared at the point 0, 1, and find the equation of this tangent line, and then graph the parabola and the tangent line. All right. So a tangent line is basically a line equation that touches our function at only one point. So how this works is that we need to calculate the derivative at points 0 and 1, and the point 0 at 1 will be the slope of our line equation. Okay, so we're going to use the second definition. So last time I stated the first definition, and the first definition was here. The derivative at point f of x, at point x, is the limit of, as h approaches 0, of f of x plus h minus f of x divided by h. So this time we're going to use the second definition. The junior tutor posted both definitions here, but we're just going to use the second definition. And it is a common known fact that the slope of the line, or the tangent line at this point, is equivalent to the limit as, is that what, 1 and 3? Okay, so I'm going to use point 1 and 3 here, not 0 and 1. The question has a typo in there. So we're going to calculate the limit as x approaches 1 of f of x minus f of 1 divided by x minus 1. Okay, so this is the other limit definition, and we're going to use this to calculate our slope. Okay, so the limit as x approaches 1 of 4x minus x squared minus 4 minus 1 squared. Okay, I don't know why there's an I there, but there's an I there. Of x minus 1. Okay, so the limit of this, if we simplify this, we are going to get 4x minus x squared minus 3 divided by x minus 1. Okay, so if we plug x minus 1 in here, we would have a 0 at the bottom. So we're going to try to factor this top and try to see if we can simplify our expression here. Okay. Also, why am I doing this in red? Okay. So if we factor the top out here, we have negative x squared plus 4x minus 3. So this is my side work here. I'm just going to factor this. This is going to be negative 1 and 1. And negative 3 and 1. Okay. So cross multiply this together, and we get 3 plus 1, which is 4. So we have our so we have our factors here. Let me just check to make sure this is correct here. Yeah, this is correct. Okay, so that means that this is equal to limit of x approaches 1 of negative x plus 1 times x minus 3 over x minus 1. And this is equal to the limit of x approaches 1 of 3 minus x, because these are canceled out, but we just factored out a negative here. And by factoring out a negative here, we can cancel these two factors out, and then we just applied a negative sign to this term here. And if we plug in 1 now, we get 2. So the slope of the line, tangent line, at 1 and 3 is 2. Okay? So now that we have found the slope of the tangent line, we can plug it into our equation here. So I'm going to switch to black now. So part B asks us to find the tangent line, the equation of the tangent line. So we're going to use the slope point formula here. So the slope point formula is y of f minus a equals the slope, or f prime of a, at x and minus a. Okay. So if we plug that in, we plug in all of them. So y minus 3 is equal to the slope times x minus the x coordinate of 1 and 3. And if we isolate for y, we got y equals 2x plus 1. 2x minus 2 plus 3, 2x plus 1. Okay, and finally, if we were to graph this parabola, so we see that our parabola has a negative coefficient of a. So the leading term has a negative coefficient. So that means it's facing downwards. So it's concave down. And the tangent point, the line of the equation is tangent to our point on the parabola 1 and 3. So you see here that the junior tutor drew the line that's tangent to 1 and 3 on the parabola, and they added the specific slope of the line, which is 2. And by doing so, we have found the line equation that is tangent to the parabola by finding its derivative at the point 1 and 3. Okay. So last time again, so the tangent line is a line that is intersecting the function at only one point. Okay. And so it's basically tangent, or is touching the graph, basically. And we found the slope by finding the derivative at the parabola at 1 and 3, and then plugging it into our line equation. So we know that the line has a slope of 2, and we also know that it touches the graph at 1 and 3. So by doing so, we find the line equation, which is y equals 2x plus 1. Okay. So other than that, the solution is correct. Good work. Okay, sorry, give me a minute. I'm just going to check on some of the background noise here. Mom, I'm streaming. I said 145. Okay, sorry about that. All right, so the next question is question number 3, and it asks us to find the integral of sine cubed of x times x dx. Okay, so the junior tutor helpfully laid out some rules that we're going to be using here. So the first rule is we're going to use the trigonometric identities, which is sine squared x plus cosine squared x equals 1. We're also going to use the derivative of a cos function, which is negative sine x. We're also going to use the trigonometric rule of integration of sine x, which is negative cos x plus c. And we're just going to use these rules of integration, which is the sum rule, the identity rule, and the power rule. Okay. So I'm going to be referencing these through the solution itself, and just follow along. If you're unsure of which one I'm using, just look at this. Okay. All right. So the first thing that we're going to do with this integral is we're just going to write it out again. So the integral of sine cubed of x times x of dx. So this is an indefinite integral, so we have to make sure when we calculate it that we have to include a constant c. So the first thing that we're going to do is we're going to use we're going to break this sine up into sine squared times sine, and I'll give you a reason why later. So we're going to break sine cubed up into sine squared times sine x times x. Looks like you forgot an x here. Oh, there's no x. Sorry, it's just sine cubed of x. We're finding integral of sine cubed of x, not sine cubed of x of x. Okay, so we break it up in this, and we're going to use our trigonometric rule of identity, which is sine squared x plus cosine squared x. We're going to isolate for sine squared x. So if you isolate for sine squared x, so if this is our rough work here, so this is our identity here, we can manipulate it in a way that we can isolate for sine squared x, which is sine squared x equals 1 minus cosine squared x. Okay. If we sub this in to our equation here, we get the integral of 1 minus cosine squared of x sine of x dx. Okay. So now we're going to use a technique called U substitution, which makes the integral that we're calculating a lot simpler to solve for, because this looks pretty complicated to us. We could try to do it, but it's pretty complicated. So we're going to call a variable u and let u equal to cosine squared of x. Oh, sorry, cos of x. Okay, so if we call u to equal cos of x, then we know that du is going to equal to negative sine x d of x. Okay. All right, so we're going to plug, and then if we isolate this further, we get negative du sine x dx. Okay. So we're going to plug in sine x dx and un into our equation here. And if we plug it in, we're going to get this integral here. So it's going to be 1 minus u squared. And sine of x dx is equal to negative du. So now we're integrating in terms of u with a negative sign outside because we can factor out any constants out of the integral itself. Okay, so now this is a much easier integral to solve. We can break it up using the sum rule of integration. So if we use the sum rule of integration, we get negative integral of 1 du, and we're going to get plus integral of u squared d. Okay? So once we use the sum rule of integration, we can use the identity rule, which tells us that the integration of a constant is just the variable itself. So we can get negative u here. And for this one, we're going to use the power rule, which states that the integral of a power function is just the power function itself with the exponent plus 1 divided by the power plus 1, or the exponent plus 1. So it's going to be u cubed, so it's going to be u squared plus 1 divided by 2 plus 1, which is 3. And this is our integral, our antiderivative. Don't forget to include constant c here, because we always have to assume that there's a constant involved. And this is the indefinite integral, negative u plus u cubed divided by 3 plus c in terms of u, right? So now that we have solved the integral, all we really need to do is sub back in our original function, which is cos x. So if we sub back u in, we get cos x, negative cos x, plus cos cubed x divided by 3 plus c, which is the integral of sine cubed of x dx. Okay. So this is the solution to it, and we use u substitution and all these trigonometric rules and integration rules to find our solution. So this solution is correct. All right, let's move on to question number 4. All right, so evaluate the definite integral of f of x equals x cubed from interval negative 1 and 1. Okay, so they, in the original question, they asked us to use a limit definition of the integral. And so they want us to calculate the integral x cubed dx. But this notation here, this integral notation from 1 is actually this notation, this integral notation is actually a notation for this entire equation, which is a sum rule or a sum function. Okay, so we have the limit as n approaches to infinity. Oops, that's not infinity. Of the sum from n to I equals 1 of f of ci times delta xi. Okay, so this notation here is basically covers for this formula here, which calculates the limit of the sum function of the function as ci times delta xi. So what is ci and delta xi? So ci is calculated by the right-hand values, and I'll get into what this all means. Okay, and delta xi equals b minus a divided by n. Okay, so where does all this come from, right? So what does the integral calculate? So the integral calculates the area under a curve, right? So many mathematicians were trying to approximate and calculate areas under the curve because they found that is very significant to many different calculations. So what they devised was that they would calculate the sum of multiple rectangles under the curve, and that will help to approximate the area under the curve. So let me explain here. So if I were to zoom out here, all right, so I'm going to put my illustration here. Okay, so let's say that we have a simple line function. Okay, so let's draw the line. I don't want. Okay, so let's draw out a line here. Let's just say it's like goes through the origin. Okay. All right, so this is our line. I don't know what the line equation is, but we're just going to call this f of x. So what they devised was to calculate the sum of uh, same length rectangles under the curve. And how they did that was, so they wanted to say, okay, first we need to define an interval where we want to calculate under the curve, right? Is interval from here to here. So they said, oh, let's make the interval from A to B. Okay, so let's say the origin is A, and this top part over here is B. So they wanted to calculate the area under this curve. Okay, so they said, okay, so let's calculate using rectangles, and let's add together, let's say, 4 rectangles. Okay, so they want to have 4 subintervals, and they want to calculate the sum of those rectangles. Okay, so if we were to split this up into 4 equal rectangles with similar lengths, right, we would have 1, 2, 3. Right, so we have 1, 2, 3, 4, and they will calculate the area of each of these rectangles, and they will calculate, oops, and then they will try to approximate the area under the curve using that. Okay. So I'm going to just draw these rectangles for now. And why I'm drawing it like this is because there are 2 widths, I guess. So they considered this to be the length first. So let me describe that. So the length of these rectangles are all similar. And if we're to bring one of these lengths down like this, the lengths will be calculated as delta xi, okay, which is basically the difference between these intervals divided by the amount of rectangles that they want to have. So in this case, they wanted 4. So by having a difference between the intervals and dividing it by 4, they were able to find rectangles of similar lengths, right? And so now all you really need to do is calculate the height of these rectangles, or the width, right? So by calculating the width of these rectangles, they were able to calculate the area by multiplying the length, the equal lengths, plus the width. So they had 2 points to choose from, right? Were we to choose from the left side or the right side? And you can choose from either, okay? So it is a known fact, I won't get into this too much, but the left side will underestimate the area, and the right value, or the right side, will overestimate the area under the curve. As you see here, if we use the right-hand side values for the height, we would see that there are some part of the rectangle that's overlapping over the curve. Okay, so CI is basically, we can use the left-hand side or the right-hand side. Here in the notation, we use the right-hand side, right? So we started out at the beginning of our interval, and we added the first length of the rectangle here, right? So if I was to equal 1, then C1 would equal the beginning of our interval plus the length. So we'll end up on the right-hand side, as you can see here, right? So the length is calculated by A plus B minus A divided by N times I, right? So if we have 4 rectangles, then we'll have C1, C2, C3, and C4, right? And these will correspond, we'll plug it into our function, and we would find our height of the function at that point. And by doing so, we can calculate the rectangles, and then we use a sum function to add up all these rectangles together to estimate the area. Okay, so now what I said before is that the right-hand sum, as you can see here, overestimates the area, while the left-hand sum underestimates. Well, they're able to come to a very, very good approximation of the area under the curve if we continue to add more rectangles together. So if we were to increase the amount of rectangles we wanted to add together, the area overlapping over the curve will continue to decrease, right? So then they wondered, what if we set the limit of this function to be heading towards infinity? What if we had infinite rectangles to add together? Then the area will be almost perfect and corresponding to the area under the curve, actually. So that's what they wanted to do, and that's where the integral came from. So this integral notation is actually representing the limit of the sum function of the areas of rectangles. Okay? And by doing so, they come to a very good approximation and actually perfect calculation of the area under the curve. So this is what the limit definition of an integral is, and this is the notation for it. Okay. So now that we've gotten that out of the way, we're going to calculate the definite integral of x cubed in terms of dx. All right. So let me zoom back in here, and let me drop. So I'm not going to use a limit definition anymore. We're just going to calculate the definite integral. Okay. So first thing that we need to use is that we need to use the integral, the power rule of integration, right? Which states that integral of a power function is just the division of the power function with exponent plus 1 divided by set exponent plus 1 plus constant c. So we're going to use that. In a definite integral, you don't need to include a constant c because we're actually just going to be subtracting that out, and I'll show you guys explicitly what I mean. Okay, so if we were to calculate the integral of this from 1 to -1 of x cubed dx, we would calculate, we use the power rule, and using the power rule, we know that it's x to the power 3 plus 1 divided by exponent 3 plus 1 plus c. Okay, so let's do this now. So this is the, oh, whoops, let me just simplify this. What am I doing? Okay, so we would have x to the power of 4 divided by 4 plus c from 1 to -1, okay? And if we were to calculate this, right, so we would plug 1 into here and subtract it by x to the power of 4 of -1, okay? So we would have 1 to the power of 4 divided by 4 plus c minus -1 to the power of 4 divided by 4 plus c. Okay? All right, so if we were to calculate this, we would see here that we have 1 over 4 plus c minus, so the -1 to the power of 4 is -1 times -1 times -1 times -1, so it's +1, so it's 1 over 4 plus, or minus c. So we see here that the c's cancel out. So that's why you don't need to include a c with a definite integral, because your assumed constant will cancel out. And all we have left is 1 over 4 minus 1 over 4. Okay? And we have that equal to 0. All right? So that's the area under the curve between 1 to -1 of the function x cubed. So this is a cubic function, right? So if you were to actually wanting to find the bounded area under the curve, because this equation does not consider the fact that that might be negative areas. So any area below the x-axis will be a negative area. And if we were to graph this cubic function out, we would see here that it's perfectly symmetrical. Let me just graph it out here and show you guys what the cubic function looks like. So the cubic function kind of looks like this, with a saddle point and it inflects to the below, right? So if we were to calculate the area from, let's say, -1 to 1, we would see here that the areas would, so if this is 1 and this is -1, we'd see here that the areas would cancel out because the integral does not consider a negative areas to be, well, the integral basically considers negative areas. So if we're adding this together, we'll get 0 basically because they cancel each other out. So if you actually wanted to calculate the area under the curve without considering negative areas, you would just multiply the integral of from 1 to 0 by 2. By doing so, you would bypass the negative area, and you would just need to multiply this because you know that this area and this area are the same. They're just negative and positive, right? So that's what the junior tutor suggested instead. But that's the definite integral of the function x cubed from -1 to 1, which is just 0. Okay, so the solution is correct. All right. Okay, so the next question reads, find the first partial derivatives of the function z equals x sine of xy. So partial derivatives pertain to multivariable functions where we calculate the derivative of in terms of one of the variables and keep the other variable constant. I won't get into too much about what partial derivatives mean, but the notation for partial derivatives is this. So it's partial z, partial x. So this means that we're deriving our function only in terms of x. So we keep y to be constant. So what they're asking us is to find the first partial derivative of this function. So we're going to try to find partial x, partial z, partial x, and partial z, partial y. Okay, so that's what we're going to try to find, and this is the notation for it. So what I said before, if we're trying to find partial z, partial x, then we're going to keep y to be constant, right? So we're just going to assume that is a number. Okay, so if our function is z equals x sine of xy, then partial z, partial x is going to be a product function, or a product rule, right? So we have to consider that this is a product of two different functions, the first function being x and the second function being sine of xy, right? So we have to do the derivative of the first function. So the derivative of the first function is 1 times sine of xy plus the derivative of the second function times the first function, which is going to be, the derivative of sine is going to be cos of xy. And also this is a chain rule, so we have to include that the derivative of yx is just going to be y. So this is going to be sine xy plus xy cos xy. So we see here that we kept the y to be a constant, and we just treated it as such, right? So we just use the product rule and the chain rule for the second part of the product rule. Okay, so now we're going to try to find partial z, partial y. So now we see here that this is just a chain rule, so we're going to calculate the derivative of sine xy, and then we're going to calculate the derivative of xy. Okay, so this derivative of sine xy is going to be cos xy. We have to make sure that we keep it x here. And the derivative of xy is just x. So we get x squared cos xy. So we see here with the partial derivative in terms of y, we kept x to be constant, and we just treated it as such. So in this case, we just used a chain rule. So we calculated the derivative of the sine function first, and then we multiplied that by the derivative of xy. Okay, so these are the first partial derivatives, right? So if we were to calculate the second partial derivatives, then we'll have to derive in terms of x or y in which way we want it to, and we have to derive our partial derivatives further. And that's where we can come to conclusions such as mixed derivatives, which are second partial derivatives are even further, which were partially derived in x and partially derived in y. So that's what we call mixed partial derivatives, but we're not going to get into too much about that. So other than that, the solution is correct, and we can move on. Okay. So the next question asks us to evaluate the limits of this function, right? So they graphed out a function for us, and they told us to evaluate the limits for a, b, c, and d, and calculate its asymptotes. Okay, so let's calculate a first. So a and b are calculating the end behaviors of these functions. And end behaviors of functions basically correspond to horizontal asymptotes, if there are any. Okay. So when we are talking about end behaviors, we want to see where the function tends towards when it approaches infinity or negative infinity. Okay, so that's what we call end behaviors. And they get their moniker end behaviors because we're evaluating the limit as they approach infinity. Okay, so the limit as x approaches infinity of f of x. So we're going to look at our right side here, right? So we're going to see that our function is actually tending towards this value of -2 here. And we can see here because it's starting to slope down, but it never touches the horizontal asymptote of -2. Okay, and for sure we can say, oh, how about later in the graph when maybe it crosses over, but we don't have that vision here, so we're just going to say that it approaches -2 as for now. a better way of calculating end behaviors is actually to have the function itself and evaluating the limit of that function. But here we're only given the graph, so we have to use what we can. Okay, so we're going to say that as x approaches positive infinity, the function tends towards -2. Okay, so let's evaluate the end behavior of the function in the other way. So limit of x as it approaches -infinity of f of x. Okay, so we see here that the function is now approaching 2 from the left-hand side. So as the function keeps going, it increases and increases and increases, but then it slowly decreases, and it doesn't really touch uh, y equals 2. So we're going to say that the left end behavior of our function is 2. Okay, so now we're going to talk about vertical asymptotes. So in any location on the graph where the function tends towards infinity or negative infinity, we call those to be vertical asymptotes. So we see here that the limit as x approaches 1 of f of x, we see here that at x equals 1, that our function approaches infinity from both sides. And this is important. The function has to approach infinity from both sides of the asymptote. Okay, a very good example of an exception is the reciprocal function, right? So if we were to have, let's say, in our notes here, f of x equals 1 over x, right? If we were to graph that out, that would look like something like this, right? Right. So we know that a vertical asymptote here is x equals 0. But we see here from the left-hand side and the right-hand side that the function approaches infinity and negative infinity. So they're tending away from each other. So this is a very important note about limits itself, is that if they are both approaching infinity from both sides, then we can say that the limit as x approaches 1 of f of x is infinity. Okay, and the notation for from the left side and the right side is this. Okay, so if the limit as x approaches 1, so we put the negative as a exponent, but we keep it on the left-hand side. So this means that as x approaches 1 from the negative side, so from the left-hand side. So we see here that this corresponds to this function approaching 1 from the negative side, okay, of f of x. All right, so the right-hand side, as you guys might suppose, is as x approaches 1 positive. I actually believe it's like this. Okay, so this means that the function is approaching 1 from the right-hand side. Okay, so that means it's approaching from here. If they both equal the same thing, maybe infinity, then the limit exists. Okay, in this case here, the limits are approaching different infinities, right? So from the right-hand side, it's approaching positive infinity, and from the left-hand side, it's approaching negative infinity. So that limit does not exist. Okay, so let's apply this thinking with the final part. So the limit as x approaches 3 of f of x. Okay, so let's see as when x approaches 3 from the left-hand side. So if x approaches 3 from the left-hand side, we see here that it's tending toward negative infinity, right? It's increasing, it's accelerating, and it's increasing, and it's increasing, and it's increasing, and it looks like it's tending towards negative infinity. Okay. What about the limit of our other function? Okay, does it also tend towards negative infinity or no? Okay, let's see. So we see from the right-hand side, our function as it comes and approaches x equals 3, it starts to tend towards negative infinity too. So that means that the limit as x approaches 3 of f of x is negative infinity. Okay. So after we finish the examples, they're asking us to find the equations of the asymptotes. And these are very good examples to explain what asymptotes are. So asymptotes are basically equations, line equations that express the behaviors of functions, basically. So horizontal asymptotes relate to the end behaviors of functions, while the vertical asymptotes speak to lines of discontinuity of functions itself. Okay, So lines of discontinuity are like x equals 1 and x equals 3. These vertical asymptotes are parallel to the y-axis, and they have equations of x equals blah, blah, blah. Okay, while the vertical asymptotes are parallel to the x-axis and have equations of y equals whatever the value of the horizontal asymptote are, right? So they describe the behaviors of the functions, and they describe what the functions are restricted to. Okay. So for the given graph, the horizontal asymptotes have y equals 2 and y equals -2. So if we were to draw a horizontal line parallel to the x-axis from -2 and 2, we can see that the end behaviors of these functions never touch y equals 2 or y equals -2. Okay? At some point, the function does equal 2 or -2, but horizontal asymptotes relate to the end behaviors of these functions. Okay, so while on the other hand, the vertical asymptotes relate to lines of discontinuity of our function. So these are values of x where the function does not exist. Okay, so in this case we have 2, and that is x equals 1. So x equals 1 does not belong in our domain on our function, as we can see here by looking at our function itself, the graph. We can see here that our functions are tending towards 1, but they never exist, or they equal infinity at 1, right? In the same way, x equals 3 is also another vertical asymptote. They describe that at this point, our function tends towards infinity. Okay? So the junior tutor also gives us another way of describing vertical asymptotes and horizontal asymptotes. So to identify vertical asymptotes on our graph, look for parts of the graph that appear more and more like a vertical line as the distance from the x-axis increases. Okay? So the vertical asymptotes will be the functions where it looks like a vertical line, or horizontal asymptotes are the parts of the functions that will look like a horizontal line. So that's another way to, I guess, geometrically think about things for horizontal and vertical asymptotes. Okay. Other than that, these solutions are correct. These solutions are correct, and we can move on. Okay. All right, so question number 7 reads, what is the limit as x approaches 0 of function 1 over x squared? Okay, so this is a reciprocal function, as we saw here, and I'm just going to graph it out real quick. Okay, so it's asking us to find a limit of a reciprocal function, so it probably looks like this. This is definitely not to scale, but f of x equals 1 over x squared, where the axes are labeled x and y. So as x approaches 0 of the function, we can see here that we can calculate the limit from both sides, okay? So we calculate the limit from one side. Oh wait, actually, you know what? This is not right. I just realized something. It's 1 over x squared. So it should be this. Okay. Okay, so if we approach the x equals 0 from the left side, so it's 0, negative, we can see here that our function tends towards infinity. And that's the same thing with our other part of our function, right? Our right-hand side of the function. As the limit approaches 0 from the right-hand side, we also get infinity. Okay, and this is because of the nature of this function itself. So as we approach 0, right, we're getting to smaller and smaller decimal and fractions, right? So the junior tutor gives us a great example here, right? So when x equals 1, right, so it's approaching from the right-hand side, we see here that the function equals 1, right? But as x equals 1 over half, due to the nature of this function itself, we're going to have the half be at the bottom. So it's going to be 1 over 4, right? Because half squared is 1 over 4. But we're going to flip that function to find its value here. So it actually equals, if x equals 1 over half, then 1 over x squared is equal to 4. right? So as we get smaller and smaller decimals, so 1 over 100, 1 over 1,000, we get bigger and bigger numbers. And because of that, we know that as x approaches to 0, we're going to tend towards huge numbers or infinity, right? So another way that you can calculate limits is by using some test values, right? So if you're really unsure about what the behavior of the function is, then you just start plugging in points as you get closer and closer to that uh, 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 value of x, right? So in this case, we're getting closer to x equals 0, so we're getting smaller and smaller decimals, right? So if the junior tutor continued, we would have 1 over 100, 1 over 1,000, 1 over 1 million, and as we keep getting smaller and smaller, we keep getting bigger and bigger values, right? And like I said before, because of the nature of this function, as the function approaches from the left-hand side too, negative values are actually mitigated due to the squared. So that's why we have them both approaching infinity. In terms of the reciprocal function, that's why we have 1 over x. For a function 1 over x, we would have something different, right? We would have something looking like this because we don't have an x squared to get rid of the negative sign, right? So that's how you calculate the limit as x approaches 0 of a function. You can use test values, or you can also just plug it in into your limit expression. So the solution is correct. Good job. All right. So question number 8. So the next question asks us to determine whether the given function f of x equals x times the absolute value of x is odd, even, or neither. Okay. So what does it mean by a function being odd? So if we have an odd function, that means that f of negative x is also equal to negative f of x. If we were to have an even function, we would have f of negative x equals f of x. And the function is neither odd or even if either of these rules don't hold. Okay? So we're going to calculate the whether or not this function is odd or even. Okay, so we have f of x equals x times the absolute value of x. Okay, so all we really need to do is just plug in f of negative x and see what we get. Okay, so we plug in f of negative x, we get negative x times absolute value of negative x. But we need to note that the absolute value function works like the absolute value of negative x is also equal to the absolute value of x. So because of that, we have f of negative x equal to negative x times absolute value function of x, and that's equal to negative f of x. So therefore, f of x times the absolute value of x is odd, because we can see here that f of negative x is just equal to negative f of x. Okay. So what these means is these relate to, I guess, symmetrical functions. So a good example of a even function is something like a parabola, right? So a parabola is an even function because f of negative x is just f of x, right? A good odd function is something like a cubic function where f of negative x is also just negative f of x. So we just reflect it across the x-axis. So these are good examples of odd or even functions. And yeah, they're symmetrical in their shape. And we now know that x times absolute value of x is also an odd function. So the solution is correct. All right, question number 9. So using the sum of cubes rule, a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. By using this identity, evaluate the limit as x approaches to 5 of x squared minus 13x plus 40 divided by x cubed minus 125. If the limit does not exist, enter d and e. Okay. So till this point, we really haven't talked about how we can evaluate limits. And this is a good question to showing some techniques of how to evaluate limits. Okay, so let's first let's first write out our limit here, which is limit as x approaches 5 of x squared minus 13x plus 40 divided by x cubed minus 125. So the first technique that we can use to evaluate limits is to simply plug in x equals 5 into our function, right? So here, if we plug in x equals 5, we have a good chance that we'll be able to evaluate the limit. In this case, we're not able to because the denominator function becomes 0, and we have an indeterminate form, which is something divided by 0. Okay, so we can't do that yet. So the other technique that we want to use is we want to simplify our function here, our expression. We can do that by algebraic cancellation. We can do that by factoring the numerator and dividing it and simplifying the numerator and denominator. We can also use conjugates to get rid of square roots or complex numbers. We can do a lot of different things, right? So these are different techniques that we can use to help us to calculate or evaluate our limit. So we're going to use the sum of cubes to help us calculate this limit. So this is equal to the limit as x approaches 5. If we use the sum of cubes here, we know that the denominator can be alternatively written as x minus 5 times x squared plus 5x plus 25. Okay, we can alternatively write our denominator as this. Okay. Next, we can factor at the top, right? I believe it's factorable, right? So x squared minus 13x plus 40 is also equal to x minus 8 times x minus 5. All right, so if we do that, then we get limit as x approaches 5 of x minus 8, x minus 5. Divided by x minus 5 times x squared plus 5x plus 25. Okay, now we can factor out x minus 5, right? We can cancel that out, and we're left with the limit as x approaches 5 of x minus 8 divided by x squared plus 5x plus 25. Finally, let's try to plug in 5 now, right? So if you plug in 5, our denominator is not equal to 0. It's actually equal to 25 plus 25 plus 25, which is 75. And the top is equal to negative 3. So now we have evaluated our limit, which is negative 3 over 75. So now we know that this function as x approaches 5 is equal to negative 3 divided by 75. Okay, so this solution is correct. Finally, the last question asks us to, using the definition of continuity, state how continuity is destroyed, or state how the graph is discontinuous at x equals c for each of the graphs. Okay, so a function is continuous at x equals c if the limit as x approaches c of f of x is equal to f of c. So this is what it means that a function is continuous. Okay? That means that the behavior as the function reaches c is equal to f of c itself. Right? So that's what it means that functions are continuous at point c. Okay? And each of these graphs are discontinuous in a different way, and I'll explain why. Okay, so first of all, let's cover A. So why is A discontinuous? Okay. So A is discontinuous because, as you can see here, that as x approaches c from the left-hand side of f of x is not the same as the limit when x approaches c from the right-hand side. Okay? So we see here that there is a jump discontinuity here, and we see here that from the left-hand side, x approaches f of c. However, from the right-hand side, we see here that f the function does not approach f of c. It actually approaches a different value, which is actually undefined on the function itself. Okay, and this goes back to saying that a function only maps one value from the domain to another value in our range. So you see here that c here is actually mapped to only one value here, but the function approaches from the left-hand side and the right-hand side 2 different values. Okay, that's why a is not continuous as c, because the limit does not equal the same. Right? The limit from the left-hand side equals f of c, but the right-hand does not, right? And we need both left-hand side and right-hand side limits to equal the same. Okay, what about b? Okay, so the limit from the right-hand side and the left-hand side equal the same thing. However, f of c is not defined on this graph. But as you can see here by that blank, this blank dot here, it signifies that f of c does not exist, right? It's restricted, right? For multiple reasons, it does not exist. So because of that, the limits, although they equal each other, they cannot equal f of c because f of c does not exist. Okay. All right. So what about c? So in c, our left-hand limit and our right-hand limit are the same. However, they don't equal f of c because f of c is defined alternatively, differently. So we see here that this graph is not continuous because although the left-hand side and the right-hand side limits are the same, the value of f of c does not belong in this graph here, and it's a separate point here. So the value of f of c is not equal to the limits from the left-hand side and the right-hand side of c. Okay? Finally, part D is just the same thing as A. The right-hand side equals f of c, right? However, the left-hand side does not equal f of c. And we need both the left-hand side and the right-hand side to equal the same, right? In this case, they don't. All right, so because of that, we cannot say that this function is continuous. All right, so these are separate reasons why the function is not continuous. For the first one, the left-hand side equals f of c, but the right-hand side, the limit of the right-hand side does not. For the second one, f of c is not defined, even though the limits of both left-hand side and right-hand side are the same, right? They are approaching the same value, but f of c is not defined. So since f of c is not defined, then we cannot say that it is continuous. For part C, the left-hand side and the right-hand side limits are approaching the same value, but it's not f of c itself. F of c is defined alternatively, and because of that, it's not continuous. And finally, for part D, the right-hand side limit is approaching f of c, and it equals f of c, but left-hand side also has to equal f of c, which it does not. It equals a different value. So these are different reasons of why functions cannot be continuous. Okay. So other than that, the solution is correct. Good job. Okay. All right.
So that wraps up today's lesson. I covered 10 questions related to derivatives and calculus and limits. If you have any other questions or concerns with your homework or tests or assignments, please submit them with OneClass and we'll get to them as soon as possible. And I hope that you guys learned something today, and I wish you guys a good afternoon. Bye, guys.